And now to push your knowledge of math a little bit, we're going to do a similar example, except without numbers for the coordinates, just a variable a. Alright, first, a charge q is located at the origin. Find the force on this charge if, and we've got three situations. So let's define a coordinate system. I'll mark off my axes here real fast, just so you can kind of get an idea. So the intersection would be the origin. And we have a charge positive q placed at the origin. So right there, we have plus q. Find the force on this charge if a second charge, negative q, is placed at coordinates a, 0. Now I'm just going to make up a distance for a, and that may actually make this too simple, but I think it'll also help you. So I'm just going to say a is 4 blocks. Okay, so a, 0 would be 1, 2, 3, 4. So that's at point a, 0, 0, and we place a charge negative q there. Now this question, the way I wrote it, I intended it to be like each one adds more complexity. So right now we want to find just the force with this setup. So let's do that now. Force on q from, and I'll even number them. This is 1 and 2, even though they are the same amount. So force q1, q2 equals k times q times q, or we can even say negative q, over, now the distance, since this is just a straight line from there to there, that distance is just a, because it's clearly just a straight line. So over a squared. And in fact, that would be my answer. It would be k, since the q's are the same, q squared over a squared, and negative since one of them is negative. But that's dealing with direction, and we can easily find that out. So positive q would be attracted to negative q, and so we would have a force toward negative q, because they'd be attracted. But that's it. That's the force so far. Now moving on, we now put a third charge, negative q, at 0, a. So 0, a would be 1, 2, 3. Since I've defined a to be 4 blocks, a up. So that's at position 0, a. And we put a charge, negative q, there. Well, now we'll need to find the force from that charge and then add them using vector addition and the Pythagorean theorem. So now we've got, let's call this the third charge, but it's just q. Force q1, q3 is k, q, negative q over a squared, which gives me negative k q squared over a squared. And those two would attract, worry about the force on positive q, so it would experience a force toward the new charge. And if we add those with vector addition, just do this on the side because there's going to be a lot happening on here. If we add those with vector addition, let's call the orange one the first vector, blue one the second vector, our resultant vector, up and to the right. So that's the direction of the force. And then we find the magnitude of the force using the Pythagorean theorem, since these make a right triangle. So the magnitude of that resultant force, which we can call c squared, equals the magnitude of the first one squared. So k q squared over a squared squared plus the magnitude of the second one, k q squared over a squared squared. Then we take the square root, so c equals the square root, k q squared over a squared, all squared, plus k q squared over a squared, all squared. Now, these two things can add together, meaning that I now have c equals the square root of 2 k q squared over a squared, all squared, which simplifies to, hold on a second, c equals the square root of 2 times, and since this part, that 2 should be on the outside there, the part that's squared just becomes unsquared by the square root, so now the square root of 2 times k q squared over a squared. So Pythagorean theorem, adding those two together since they form the sides of a right triangle. That's the current force, and it is up and to the right. So that's the current force on the original charge. I've rearranged things a bit just because I needed some more room. Now we put a fourth charge, positive q, at a comma a. Right there. This is positive q, and it is at a comma a. The tricky part now is we've got to get the distance correct, so let me start this and I'll show you. So if we're looking at this fourth charge, which we can call q4, f q1 q4 is k q q over. Now, the distance isn't a squared, because if we draw a line from the original charge to the new one, that's a diagonal, with, if we were to complete this triangle, with sides a and a. So side length a, side length a. So the length from the charge at the origin to q4 is the hypotenuse of a triangle. So again, we've got to use the Pythagorean theorem. So our distance there will be, distance squared will be a squared plus a squared, which would be d squared equals 2a squared. Take the square root of both sides. You get d equals the square root of 2 times a. So that's our distance, the square root of 2 times a. We square it. And so force q1, q4 is k q1, should be k q squared, q times q is q squared, over square root of 2 squared is 2, a squared is a squared. So that's our force. Now we've got to find the total force with the other vectors. But what's convenient here is notice that the direction will be exactly opposite the direction of the other two added together. So think about this. This is a positive charge, up here q4. Original q was a positive charge, so it will push away. Now when we found the resultant vector, notice it's the exact opposite direction. So those two form a line, the resultant vector from the first two and the new one. And if two vectors form a line, you can simply add them together. You don't need the Pythagorean theorem. Since they're in opposite directions, we will, however, subtract them. So we can do F, Q from all of them. So the force on Q from all of them will be what we found for the first three charges. The square root of 2 times k q squared over a squared, minus, because I'm just going to pick this way to be the negative 1, minus k q squared over 2a squared. And that's an acceptable final answer. We could do some factoring there, but that's it. And that's a lot. Just dragged you through a lot of math and a lot of Pythagorean review. Might need to try that again. Might need to watch that again. I especially suggest trying the post-reading question. It's very similar to the lab tomorrow, and you really need to be able to do that question. Think a lot about forces, and be sure to draw lots of free body diagrams. Other than that, see you tomorrow.